All right, we are looking at the trigonometry unit, lesson 3. The objective for that is to be able to use trigonometric ratios, that's sine, cosine, and tangent, in a right triangle to find the angle measure, if you know, or an angle measure if you know the lengths of two sides in that triangle. First up, we want to talk about inverses a little bit. We've done that in class a bunch. One of the key items is that you've learned that the domain of a function is the range of its inverse. And the range of that function is the domain of the inverse. So the x and y coordinates interchange. Functions we've looked at and found the inverses of would be f of x equals x to the third. The inverse of that is going to be x to the 1/3. G of x equals e to the x we've actually not looked at. We are doing things in a little bit different order, so you haven't seen that one. But for future reference, the inverse of e to the x would be ln, which is the natural log of x. We'll get that next semester. H of x equals the square root of x. Again, we have to restrict the domain there so that the square root we don't take of a negative. The inverse of that would be x squared. All right. Turns out that the three trig functions, sine, cosine, and tangent, are also functions. If I tell you an angle from 0 to 90, you're able to find the ratio in that triangle for that angle. And again, doesn't matter the length of the sides, that ratio will always be the same. The domain for the trigonometric functions is an angle. When we get the output, that will be the ratio of the specific sides that define that trig function. The trig functions also have inverses. For the inverse trig functions, the input will be the ratio, or the fraction that the sides are, and the range will be the angle. This is important. The output of the inverse trig function is an angle. That should help us reach our objective for the day. All right, something I want to do in addition here is this. If we have input for the function, it's an angle. Output is a ratio. If we go to the inverse, again, x and y interchange, so the input will be the ratio, and the output will be the angle. So that's what we'll be looking for today, is that angle. Right? So we have sine x. Its inverse is inverse sine of x. Again, that's sine of the negative 1 of x, but we don't read it that way. We read it inverse sine x. Cosine x and inverse cosine x in line 2. And then tangent x and inverse tangent of x in row 3. To find the inverse trig buttons on your calculator, you can use those to find the inverse sine of 1/2. Again, if your calculator is set up to use degrees, which it should be, it should tell you that the inverse sine of 1/2 is 30. So when the ratio of the sides, right, opposite side to the hypotenuse, is 1 to 2 or 1/2, the angle measure in that triangle has to be 30 degrees. All right, so we're going to pause for a sec, and I'll be right back. All right, so first example, how to use trigonometry to find an angle measure. First, we have to decide which trigonometric ratio would be the easiest to write with the information that we know. From angle theta, right here, we have the side opposite, and we have the hypotenuse. Again, it's the hypotenuse because it is opposite the right angle. We don't know the third side, but from the looks, we can tell it's also the longest side. All right? So we write sine theta equals opposite over hypotenuse. That's 6.14 over 6.53. You can either do the division with your calculator, or, if you so desire, you can actually substitute in here, when we're solving, the actual fraction. That way you don't have any round-off error, but you would need to use parentheses. Okay? Either way, theta is going to come out being 70.098. So again, you have to find that inverse sine on your calculator. If you're in a CX, you'll go to the trig button, which is just left of the 7 key. If you hit it, you just use your navigation arrows to get to the inverse sine, in this case, and then enter your fraction, enter, and you should be golden. So let's try a couple of these together. First up, we identify where theta is. That's looking good. Then we would try to decide what the 9.86 and the 14.3 represent, opposite, adjacent, and hypotenuse. Again, I think easiest would be to look at the hypotenuse. That's opposite the right angle. We know that this is the opposite side, so the one left over has to be the adjacent side. So we would have adjacent and hypotenuse. I would think of that as cosine is the adjacent over the hypotenuse. So we would write cosine of theta equals adjacent side 9.86 divided by 14.3. To get rid of cosine, we have to use its inverse. So we would write inverse cosine of the cosine of theta, and then we would also take the inverse cosine of the right side. So we would have what? Inverse cosine and cosine cancel each other out. One does, the other undoes. And then we would have to type inverse cosine of 9.86 over 14.3 into our calculator, which would give us the theta, or the angle measure, equal to 46.4 degrees. All right, so there we go, 46.4. Continuing to the next problem, we would take a look at where beta is in this case. Instead of theta, we have beta. Again, the side opposite, because our angle bisector would run into that side, so 17.9 is the opposite side. Hypotenuse is over here, so the adjacent side must be 8.71. So we have opposite and adjacent. In my head, that pops up as TOA, so we have tangent. Let's write the equation. Tangent of beta equals the opposite side, 17.9, over the adjacent side, 8.71. And to get rid of the tangent, we would take the inverse tangent of both sides. So the inverse tangent of the tangent of beta equal to inverse tangent 17.9 over 8.71. Don't forget the parentheses on that one. Inverse tangent, tangent cancel out, so we have beta equals, if we type that into our calculator, we should end up somewhere near 64.1 degrees. All right, so last two examples. Again, we're looking at beta. From there, we would have the hypotenuse, which wouldn't change no matter which angle we were looking at, and this would be adjacent because the side opposite is over here. So again, adjacent hypotenuse, that gives me or cosine. So I would write cosine of beta equals the adjacent side, 8.36, over the hypotenuse, 19.11. Inverse of cosine, we would write as cosine of the negative 1, which is right inverse cosine, of the cosine of beta equals the inverse cosine of 8.36 over 19.11. Again, I'm not going to change that to a decimal because we'll get round off error, so I would just type that into my calculator, making sure I use the parentheses. If we do that, 64.10 or 0.1 degrees, sorry. Beta is 64.1 degrees. Let's move on to the last one, see if I can manage this. We have theta here, which gives us the side opposite. And since the hypotenuse is opposite the right angle, we have the adjacent over here. Opposite over adjacent, I'm looking at tangent. So tangent of theta is 8.78 over 14.62. And I'm going to change colors to go to the inverse. When we go inverse tangent, it didn't change colors. Inverse tangent of tangent of theta equals inverse tangent of 8.78 over 14.62. Inverse tangent, tangent undo each other, so we have just theta. And we end up with, I believe, something like 30.98 degrees. If you rounded around that off to one decimal, that ended up being 31 degrees. Actually, 31.0 if you want to do the significant digits there, I think. Actually, it should be 2 digits, maybe. But that would be that. What we'd like you to do at this point is take a look at the summary and write up what you think you saw. What you think you thought.